At first, there was a vastly thick mass of issue. This mass went through a blast that brought about the arrangement of atoms, particles, stars, and galaxies that we can observe today. For many years, this has been the explanation presented by physicists. Anyway, later research has presented a new point of view that suggests the universe doesn't have as early a beginning as at first accepted. Rather, it could be part of a repeating cycle in which the universe goes through a progression of cycles of development and constriction, conceivably in an endless circle. Brian Cox, a famous physicist, feels a little wary about the theory of how things came to be, contending that something can't emerge from nothing. This scrutinizing adds an interesting component to the conversation. What's more, research from the James Webb Telescope has uncovered data that goes against the possibility that the Big Bang denoted the absolute start of the universe. This prompts the basic question: if the Big Bang was not the start of the universe, then what was? Join us on this excursion to the origins of the universe, where we will explore the boundaries of the Big Bang and answer this inquiry and more. If you are keen on keeping up to date with news about the universe and its environment, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Researchers have developed a detailed understanding of the universe in its earliest stages, known as the theory of how things came to be. According to this model, the universe was much smaller, hotter, and denser than it is today. Around 13.8 billion years ago, during that period, all the elements that make up our reality were formed in a matter of minutes. In this hypothesis, our universe, including stars and galaxies, was once as small as a peach and had a very high temperature of over a quadrillion degrees. Strangely, this surprising story aligns consistently with all current observations. Astronomers have explored everything from the leftover electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything concurs with the predictions of the Big Bang. To the best of our knowledge, this portrayal fits the reality of our universe impeccably. Anyway, regardless of its apparent power, we realize that the theory of the universe's origin isn't the complete picture. There's a missing part of this riddle, and that part is an understanding of the principal moments of the universe. This challenge is due in large part to the limitations of the actual theories we currently use. The combination of general relativity and high-energy particle physics furnishes us with a significant theoretical framework. However, as we delve deeper into the initial moments of the universe, the mathematical complexity increases significantly, reaching a point where our current methods can't provide meaningful solutions. One sign of this difficulty is the presence of a singularity, a point of infinite density at the beginning of the Big Bang. This idea suggests, literally, that the universe was once packed into an infinitely small and dense state, which seems absurd. To address this challenge, we need to explore new frontiers in physics, fostering an approach that overcomes these constraints and provides a more complete understanding of the first instance of the universe. Our current tools and theoretical structures are not robust enough to address this challenge, so we need to develop new physics that can include and explain gravity and the other fundamental forces at extremely high energies. This is precisely where string theory comes into the picture. This theory seeks to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. Generally, string theory posits that it can provide an explanation for the initial moments of the universe. Within string theory arises the concept of an aeon, which takes its name from the Greek word meaning setup or age. This idea suggests that the Big Bang, as we know it, was the result of a prior event, implying that it was not the absolute beginning but perhaps part of an ongoing process. Extending the concept of an eonic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for centuries, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it endlessly oscillates between big bangs and collapses in an unending cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the famous physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was fascinated by a striking mathematical relationship between the early universe, characterized by extreme density, heat, and minuteness during the Big Bang, and the future state of the universe, which is characterized as very cold, expanded, and devoid of matter. The theory proposes that these two states become mathematically indistinguishable when pushed to the limits. Despite its seemingly incomprehensible nature, the absolute absence of matter could be the driving force behind the creation of all the matter we see in the universe. According to this perspective, the Big Bang starts from what remains almost imperceptibly after all the matter in the universe has been consumed by black holes that eventually vanish into scattered photons in a vast void. The universe emerges from what, from another viewpoint, essentially approaches nothingness. Although this nothingness is still a form of something, it is a physical universe but an empty one. The mystery lies in how the same state can be interpreted as both a cold void universe and a dense universe, depending on the perspective. The key to this understanding lies in a complex mathematical method called the conformal change, which is a geometrical transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the cold void state and the hot dense state can be connected through the scale change, aligning their spatiotemporal structures despite their differences in size. Anyway, Penrose contends that the concept of time loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events transpires from an old cold state to a young hot state. The presence of the hot and dense state is the result of the past cold and void state. However, this causal relationship does not follow the usual pattern in terms of time, since in these extreme states, both size and time lose their conventional meanings. The cold void.